Can you guys hear us? I forgot to turn on the microphone. I hope right now you can hear us.
The light is white, so hi Zoom people.
Are you able to see anyone from there? Probably not.
What?
Are you able to see anyone from there? No.
Well, it's just a camera. I can look into the dark void, but I can't give any feedback. That's fine. I don't need to.
What you can see?
I can see how. Well, I can move to make sure that now I can. Hi Howard. So once people with the coffee and tea come back, then we'll start.
Okay.
Yeah. So Juven, just in terms of the camera, does the camera automatically track or does it?
Oh, sure. I'll try.
Okay, track.
Yeah. It should be whiter. You think it's whiter? Yes, it can. That's it. All right, welcome everyone. We are very happy to have Professor J.C. Thaler from MIT, and he will be speaking about what observables are safe to calculate. So please feel free to ask questions during the talk. Let's welcome Jesse.
Thanks very much, Juven. Great to be here. I think this is actually my first time in the CMSA building, so great to go down Mass out and visit you all today. I've decided today to give a Blackboard talk. I haven't given a Blackboard talk in a long time. For those of you who know my trajectory, most recently I've been serving as director of the Institute for Artificial Intelligence and Fundamental Interactions, institute that's trying to bring together the AI and the physics communities. And when you're trying to talk about things about AI, oftentimes you need visualizations and pictures and movies and things. And so it's been a long time since I've actually picked up a piece of chalk. So this is practice. And partly this is practice for me because the graduate students at MIT had a petition for me to reteach my class on supersymmetric quantum field theories. And I feel like I should probably get back in the habit of learning how to use this particular implement for communication. So the title of my talk is What Observables Are Safe to Calculate. Safe is a term that has a technical meaning, which I'll explain to you in case you're not familiar with that in the context of quantum field theory and collider physics. And the starting point for this is a question that comes up in the context actually of a workshop that's happening here at CMSA regarding scattering amplitudes. And if we're thinking about quantum field theory, in particular thinking about quantum field theory as it pertains to collider physics, we usually think about the scattering amplitude as kind of the primitive object that we like to study in a quantum field theory to describe how a system evolves. So you start off some beams, A and B, you bring them into collision, some number of particles come out, and if you understood the mathematical structure of that scattering amplitude, you would say that you would understand the predictions that would come from that particular quantum field theory. So that's a nice thing to think about from a theoretical perspective. But if you actually want to compare to experimental measurements, an experiment can't actually calculate or measure rather a scattering amplitude directly. The thing that you're actually measuring in an experiment is a cross section. So you have to take this object, you have to square it. This object is a function of phase space. You have to integrate over all possible phase space configurations. There's some kind of flux factor that you have to do to convert this into a cross section. And then the cross section isn't just an object that depends on the amplitude. You have to make a choice. You have to say, I want to measure something. You have to choose an observable. That observable is a function of phase space. You involve that with scattering amplitude squared, and that gives you the cross section for that particular observable. And so from a more experimental perspective, the predictions that come out of a quantum field theory are the predictions for what this cross sections would be. So there's a kind of interesting philosophical question that you can ask. You know, if someone gives you a whole bucket of cross sections, that is, you've made a bunch of choices for what observables you want to measure. One second. Then you can ask from that set of cross sections, can you tell what quantum field theory you're dealing with? That is, are the predictions that come out of all these cross section measurements, are they unique for a particular quantum field theory? And that's an interesting philosophical question, which I'm not going to answer in this talk. Rather, I'm going to be thinking about it in the other direction, thinking about, okay, if I have a quantum field theory and I restrict myself to be making predictions that are perturbative. That is, I want to think about doing kind of an order by order expansion in some couplings. From that, can you actually make a prediction for cross sections? And there are certain cross sections and there's certain things that you can measure for which it's not safe. That is, it's not true that in perturbation theory you can get an accurate prediction. And we want to understand in this talk a little bit about what observables can I choose such that I get reliable predictions in quantum field theory. So this is going to be where we're going in this talk. So yes, the question.
Yeah, I was just exactly want to ask, can you say a little bit more about this observable? It seems nothing included in the textbook.
That's right. So when you think about an observable in quantum mechanics, what do we mean? We mean some Hermitian operator whose expectation values are, for example, something that you could predict. And so this secretly is, or can be viewed as, an operator. The way that it's written right here, it doesn't look like an operator. But if you wanted to look more like an operator, you can imagine an operator, some kind of measurement operator. And what is it? It's going to be some kind of sum or integral over phase space. I guess this also has a sum that I'm missing where n has to go from 2 to infinity. Some integral over phase space of some f observable on that phase space point, and then a Brock f that corresponds to exactly the particles corresponding to that phase space configuration.
Usually would include the observable in the definition of the scattering amplitude, right?
No, it's always to the scattering people. The typical way we do it is that we choose these things as the elements of a Fock space.
Right.
So these are Fock space elements, but the observable really is basically the coefficients in front of this this outer product. So we do not include the observable in the scattering amplitude
Well, it
typically.
depends on your scattering setup, right?
Right. So the traditional thing to do is to think about Fock space elements, and here, I mean, of course, you could try to measure each individual Fock space element. So you can imagine this being some kind of delta function that picks out a particular phase space configuration, and that is super unsafe. Safe observables are ones for which this actually involves a non-trivial combination of different Fock space elements, which we're going to see in a moment. But when we talk about scattering amplitudes, we actually don't think about the observable. We typically think about what the Fock space is. When we're thinking about observables, we usually that's usually external to this. And in particular, these observables could make sense even if I had no, like, I don't even need to know my quantum field theory to be able to measure this thing. I could just tell an experimentalist, hey, make this measurement independent of what the theory prediction is for the amplitude squared. Does that more or less answer your question? No. Of course, you could choose different basis elements here. You could say, oh, well, I don't want to measure a scattering into these Fock space states. I want to measure a scattering into some like coherent states or something like that. But then to convert that into something that an experimentalist could use, you would then have to convert it into a language where an experimentalist would say, ah, yes, I have measured that particular phase space configuration. And unfortunately, the sensors that we have at colliders aren't typically sensitive to anything other than things that are close to Fock space elements. Okay. So again, philosophical question, can you actually determine a quantum field theory from its cross-section predictions? And then, so that's interesting question. Here we're going the other direction. Can I actually make predictions, like give me estimates for what a cross-section is from perturbative quantum field theory? And though this isn't the focus of this talk, as a kind of an aside, I do want to mention the extent to which these two questions are kind of related to each other. And they're maybe more closely related than you might think. In the following sense. So let's just say we don't know anything about the universe that we occupy. We're pretty convinced it's a quantum field theory, but we don't even know what the states of that quantum field theory really are, or what all the operators are in that quantum field theory. And you're trying to figure out which universe or quantum field theory you occupy. And let's say for some reason you're able to actually create beams of particles to collide them together. So at least you know how to smash stuff together. But you don't necessarily know all the different things that can come out. You don't even have sensors that can tell me about all the various elements that can come out. And then you're trying to figure out what universe that you occupy. Well,
by the way,
yeah.
just a quick comment.
Yeah.
I think the quantum field theory, this type is actually more like consists of the particle excitations, right?
Right.
So,
That's right. So this assumes
Yeah.
that I have some kind of quasi-particle long-range description. So if I have a theory for which I can't think about single particle states as being my asymptotic states,
Right.
then obviously this completely breaks down, which I'm going to come to in just a moment.
right, like a topological quantum field theory.
So for example, that would be one for which you have a very difficult time describing in this
Conformal
language.
field theory.
What?
How about conformal field?
And conformal field theory is another example, which I'm going to come to in just a second. Yes. Okay, so for a generic quantum field theory, as in you might not even know whether these things exist, or what those states are, but something that we think is quantum field theories that have the properties of corresponding to having a Poincare symmetry. There's one operator that you kind of guaranteed that will exist, and that's the stress energy tensor. And so you can ask the question, if all I had was access to the stress energy tensor, what types of cross sections could I measure? And there's a kind of a beautiful story that started off with Katchaf's work in the mid-1990s, saying that there's one way of repackaging certain cross sections in terms of the stress energy tensor. In particular, you take the stress energy tensor T mu nu, the mu component, we're going to choose 0, so we're going to study the energy. We're going to take the spatial components I, pointing in some particular direction. So T0I, so if I imagine having my collision here, I'm going to have a sensor at some angular location defined by my n hat direction. And then the stress energy tensor is a function of space and time. And what I'm going to do is I'm going to imagine an idealized experiment where I do this collision and I make a measurement off at infinity. So my time component will be taken to infinity, take the limit as my time component goes to infinity, or my radius that I'm making my measurement off to infinity. The spatial component, I want to take the stress energy flux that's going basically off to my detector at infinity. So this direction here, R, will be sent to infinity, and pointing in the particular direction that I want to look. And then there's some flux factors here, which I'm not going to, or normalization factors here that I'm not going to put there. But this operator, which is called the energy flow operator, is an operator that basically measures how much stuff I have going in the sense of stress energy. How much stuff do I have going in a particular direction? And one of the contributions that I made to this area is that you can also think about what speed you're going at. So you can imagine having a collision, and if you pull this thing away at the speed of light, then when I have this collision, I'm going to capture, for example, all the photons going off. But if I have it going at some subliminal speed, I'd be able to capture particles going at different velocities, basically particles that have different masses. And so this object here, the energy flow operator, this is an operator that you kind of know every quantum field theory will have in it. And you can then try to make predictions for a cross section that corresponds to how much stuff is going in directions n1, n2, n3, and so on. And these are called multi-point energy correlators. So I have detectors, n1 here, n2, n3, and so on. And then I'm basically asking how much stuff is correlated as I move these angles around for how much stress energy is moving in these various directions. And this thing has an operator definition involving this energy flow operator. And so on. And this is something that, again, with this broad heady story up here, you can show that this expectation value of these energy flow operators that corresponds to something that can be mapped onto a cross section. And this is something that you can, or we think we can measure in basically any quantum field theory, including a conformal field theory. And this is what Hoffman and Maldacena argued in 2008, which is that this is a thing that even in contexts where the S matrix might be ambiguous, at least this is something that we think that we can measure in any quantum field theory, even a conformal one. And so you can ask the question, you know, is a theory uniquely determined by its multi-point energy correlators? And by the way, if you haven't had Ian Moult come speak here, he's a proponent of this energy flow story. And this energy flow story has a long history, going back even to the 1970s. But Ian Moult at Yale is one of the people that's been really pushing and advocating for this, and he has some really cool things to say in that direction. Okay, so again, is a theory uniquely determined by its multi-point energy correlators? That's one question you can ask. But for this other question here, it turns out that most observables built out of this energy flow operator satisfy the property of being safe. That is, they are computable in perturbation theory. And so while we won't restrict in this talk to only to observables that are built out of the energy flow operator, it's kind of interesting that this is a nice primitive object to think about for thinking about characterizing a quantum field theory, because it is something that both has a non-perturbative definition that you could get even in a conformal field theory, but also is something that you can compute perturbatively. Okay? Yeah.
That really depend on the order.
So these because it's the same operator here,
Okay.
and it's often infinity, they'll commute. So the order doesn't matter in this particular case. So of course, there's a cool thing that happens when you start bringing these N1 and N2 really close together. Right now, you need to start thinking about operator product expansions and fun things like that. But for widely separated N1 and N2, you expect them to be commuting, at least in the limit that R goes to infinity. Okay, so you might say at this point, well, wait a second. Like there's other operators or facts about a quantum field theory that surely must be safe. I mean, here we're talking about the stress energy tensor, but surely there must be other things that would be safe even in the context of perturbative quantum field theory to compute. Like, why am I emphasizing just the flow of energy? So again, this is saying that energy is a key object. But there's other things that quantum field theories have, and you might say, well, geez, why just focus on the flow of energy? Why not also think about other types of flows? Maybe those are also well defined. And so you can ask the question, you know, what about flows of charge? Let's say you convince yourself that you have some either exactly or approximately conserved current, and you convince yourself, yes, I have some U1 or maybe some non-abelian asymmetry. You know, what's stopping me from making calculations of that, the flow of charge? And it seems like in our universe, we don't ever get ourselves concerned about being able to measure the motion of electrons or even when we're thinking about let me just focus on the electron case. Like no one is concerned about how can I really tell that this amount of current is going through this wire, right? And so why am I going to tell you in a moment that charge is something that's not safe to calculate, right? And that charge is actually a complicated beast. And the reason is that in the limit that we're going to be caring about in collider physics, so in the limit that let's say the electron mass goes to 0, in that limit, charge is, or charge flow, that is the thing that I can measure in a collider experiment where I have detectors that are far away from my collision point. Charge flow is unsafe, which is kind of a surprise. And so why is that? So imagine that someone gives you an electron and says, hey, I have my electron, it's moving around. I would like to measure where that electron is going. And of course, where did this electron come from? It came from some other scattering process, you know, A and B coming in, some collision happens, stuff comes out, and now my electron pops out. Why is this ambiguous? And the reason this is ambiguous is that electrons will radiate. And so an electron can radiate, for example, a photon. And so now this initial electron that you had here is actually off shell. And let's say that photon is radiated at an angle theta with respect to the outgoing electron that's associated with it. And if I then look at the scattering amplitude, or particularly the amplitude squared associated with this process, there's a propagator here. And when the dust settles, you find that this process diverges as theta goes to 0. And so there's what's called a collinear singularity. Associated with the fact that there's basically an infinite, in quotes, probability that an electron will radiate a photon, at least in the limit that the electron mass is 0. When the electron mass is finite, this gets cut off. And so that means if I'm saying, oh, I really want to measure the amount of current that's flowing in some direction, well, that charge can radiate a photon. The photon doesn't carry charge. The electron does, the photon does not. And if the photon carries away any of the energy, then the current is changed. And so this is something that is unsafe just to compute this. And you need to build a safe observable. For a safe observable, what you would do is you would say, take this configuration, the singularity that's appearing here in a perturbative calculation. So again, this is a perturbative singularity. Is canceled by loop diagrams that involve the electron going along and emitting a virtual photon. And these two things need to be combined in some way in order to get something that's finite. So that this is a real emission singularity has to cancel against a virtual one. But if you just try to measure the charge flow, perturbatively, you'll find infinities. Okay, so that's one type of singularity that we have. And then another type of singularity that we have is known as a soft singularity.
By the way, I have a question.
Yes.
So there's one thing is physically you measure some observable.
Yeah.
But that observable you want to measure should be finite anyway, right? And there's this, another thing is like due to your formalism of the field theory, maybe some computation might be safe to compute.
Right.
So here you are trying to emphasize the second one.
Oh, good. So here I am emphasizing so there's actually both of these things turn out to be related. So here I'm measuring, emphasizing perturbative calculability. Of course, non-perturbatively, you can do whatever you want. Non-perturbatively, you know what all the states are, you just get some numbers, that's fine. And then you have to specify the details of how you make your experimental measurement. But here I'm emphasizing perturbative control. Again, non-perturbatively, there may be another definition. The reason why this matters experimentally is that actually telling an experimentalist what their device is measuring in the language of quantum field theory is actually challenging. And so strictly speaking, if you're saying, what is a device doing that's measuring charge? Like, it's some funny combination of this plus other processes. It's a complicated thing to describe. And observables that are safe to calculate, that is, have a well-defined meaning in perturbative quantum field theory, those are also observables that at least tend to be well-defined in the context of, the mapping between what an experimentalist measures and what a theorist calculates, that difference tends to be small. So there's another singularity, a soft singularity, and this is, in this particular example, this would be coming from the fact that I have my electron radiates a photon, and let's say that photon splits to an electron-positron pair. Electron-positron pair. And this amplitude will have a singularity when the photon carries a small amount of energy. And again, we're focusing on the electron mass goes to 0 limit. So when the electron mass goes to 0, this photon can go arbitrarily small in energy, and I get this soft singularity. I put it in quotes again, a perturbative soft singularity. And this impedes the computation. Now, you might say, come on, in practice, we know that the electron actually has mass. And so each of these singularities are regulated by the electron mass. But what you end up getting is when you do integrals cut off by the electron mass, large logarithms, and those large logarithms can spoil the convergence of your perturbative calculation. Okay, so This is why charge flow is not so easy to measure. In fact, most observables that you would write down are not safe, and you have to work hard to make sure that your observable is safe. So, since the 1970s, we've been asking the question, what is safe? And what do we even mean by safety? What's the definition of that? And one answer is that most things built, most observables built out of the energy flow operator, that these observables tend to be safe, not always, but they tend to be safe. Things were built out of other types of currents tend to be not safe. And the language of safety, usually you'll find in the literature that people talk about observables as being infrared and collinear safe. That's the language that you'll see in the literature. The infrared part corresponds to the soft singularity. The collinear part corresponds to the collinear singularity. And aficionados in quantum field theory complain sometimes because this should really be called soft and collinear safety, because infrared can correspond both to the small angle limit and the small energy limit, but we are stuck, sadly, with this term IRC safety. And that's the way that we usually talk about things in collider physics. What observables are safe to calculate? That is, what observables are infrared and collinear safe. Okay.
Oh, by the way, just still go back to my previous question. So
Yeah.
should a observable, as long as it's gauge invariant operator,
Yep.
somehow maybe there should be some design in the experiment you can try to measure it. But then when you say safe or not, it's really a perturbative curve.
It's really perturbative, absolutely. So as we said, if you just have some gauge invariant operator whose expectation value you want to compute, great, you can go do that. And what you'll find is that that observable will be either one, dominated by non-perturbative physics, or two, the mapping between that and what you're doing on the experimental side is not so clear to figure out. It's not necessarily a problem, but it is a problem if you are trying to make perturbative predictions. And unfortunately, we don't know how to do generic non-perturbative predictions in quantum field theory, at least not in Minkowski space.
Is there some way that I can ask about superconducting substances that appear to have current? I wrote out my question in the chat if you want to read
Okay,
it.
yeah.
You can just
Yeah, so say it again.
repeat the thing in your chat because it's not seen by Jesse right now.
Yeah, so what was the question again?
The question is, for superconducting substances, you apply an EMF, a plus and a minus, and then magically you get a current appearing at the plus terminal, and you get a repelling of magnetic field, and there doesn't appear to be any quantum explanation of it.
Yeah, so maybe one thing to emphasize for my talk here is that I'm talking about doing calculations in quantum field theories, assuming that I know what the correct vacuum state of my theory is, and that vacuum state of my theory preserves Poincare asymmetry. Stories change if I'm in a different phase. For example, if I'm in a material or if I'm at temperature, then the definition of what I can or cannot compute in quantum field theory changes. But here I'm imagining zero temperature, and basically I know what the vacuum structure of my theory is, yeah, that's the context that I'm in. Of course, it becomes a very interesting question when you now start to ask about the phase structures of quantum field theories. But here I'm assuming that I'm in a relatively trivial phase. In the sense that at long wavelengths, at least perturbatively, I can describe the long wavelength modes as if they were single particle states that preserve Poincare asymmetry. And that's going to be the setting.
A bulk superconductor. What if you had a bulk superconductor like a cuprate in a sphere form, and you put EMF across it, and then you suddenly found that magnetic fields were repelled, and you found there's a current going through it without resistance, which indicates the current isn't traveling through this substance.
Right, and I would say, at least in the context of this talk, I would say I don't know how to deal with that case because you're talking about putting in a background field, and here I'm imagining that my background is the vacuum.
Okay,
but it's an interesting question. I would just say, just in general, the definition of charge is subtle, and actually the phase transitions that you're describing, actually this is our one way of understanding why charges are subtle. But I'm not going to be able to give you a more satisfying answer than that. I'm sorry. Okay, so I've been thinking about infrared and collinear safety for a long time. Again, it's been thought by the field since the 1970s. And as I'll explain later in my talk, I got yelled at by some of the people who have been working on this for a long time, where I proposed an observable that I claimed that I compute perturbatively, and they said, no, you can't. And I said, yes, I can. And they say, no, you can't. And it came down to the fact that, well, what observables really are safe to calculate. And so I'm not going to give you, my whole CV of papers that are addressing this, but let me just mention 3, of which only 1 or maybe 2 of these I'll actually be able to talk about in this talk. So the first one is a paper with friends of mine who have passed through at various times at Oxford University. And this is asking the question kind of related to charge of what would you even mean by the definition of an electron if you want to actually define electronness despite the fact that you have these collinear and soft singularities. So if you have this electron, there's a collinear singularity for it to split into an electron and a photon. And nevertheless, we still have this notion that electronness is useful as a concept. How would you actually build an algorithm that still gives you nice perturbative predictions? And what we showed in this paper is that at least up the perturbative order of the coupling to the 6th power, that there is a particular definition that is complicated and technical, a definition that allows you to define electronness or even photonness in a way that is finite. And we proved that finiteness up to alpha to the 6th. Now, whether that's useful is a different question. But this is saying, like, despite the fact that charge is generically hard to define, here's a context that even if you had massless electrons, you'd be able to do it at least up to a certain perturbative order. Okay, so that's this paper that I'm not going to talk about. The paper that we're going to go to next is a paper that is trying to address this question of infrared and collinear safety in a machine learning context. And oftentimes we think about machine learning as like black boxes that are hard to interpret. Here we're going to use that black box nature of the machine to actually help us understand more about what infrared and collinear safety is and what observables are safe to calculate. And then depending on how much time I have, this is actually an answer to the question, this last paper. So the previous paper about machine learning was with Ben Knott and Sam Brightoni. And this paper from 2020 with my former students, Patrick Kaminsky and Eric Metodiev, that's actually an answer to this question, what observables are safe to calculate. And this answer to this question is in the context of actually what's known in the machine learning literature as optimal transport theory. And again, depending on how much time I have, I can tell you a little bit about that. But sometimes this paper I'm going to focus on, one, because it's most recent, but also it kind of gives you a more visceral understanding about why this is a problem that needs to be solved. And let me just give you the punchline. So the punchline is that safety, and again, this is in the context of perturbative safety, is not a yes/no question. It's not like you can say these things are safe and these things are unsafe. It's not that. Rather, safety is really about control, perturbative control. And actually, let me just write out that word. And safety is about perturbative control. And moreover, a better language than safety, that in some sense, the hints of this were already there in the literature in the 1970s, but it took this language of optimal transport to really make it clear, is that safety is really about smoothness. That it's not about a yes/no thing, it's about, if I have a function, how smooth is it? And how smooth is it in the vicinity of perturbative singularities? And then smoothness is something that, as we'll see, we can just like see directly in the context of machine learning. We can just, machine learning, we can imagine constraints that can make things more smooth. Or smoothness actually has a formal definition in optimal transport theory which then allows you to categorize all the various observables that are out there by their degrees of safety. So instead of saying what observables are safe to calculate, it's more like to what degree is a particular observable calculatable in perturbative quantitative. That's the real thing to look at. Okay, so let me just pause here and just see if there's any questions before I now start describing kind of how we encountered this most recently. It's kind of surprising, 2023, end of last year. I thought I understood this topic, and then machine learning came and surprised me.
So I
Yeah.
guess I want to ask, I mean, we know how to deal with it, the evidences and linear evidence and science. So what are we able to?
Yes, you thought you knew how to deal with it, and I'm going to show you a machine learning example, which shows that you do not actually know what you're doing. And when I say you, I mean me.
Yeah.
Right? That I thought I knew what it meant to be safe, and I was wrong. And what it took was a machine learning architecture to like, in retrospect, it's totally obvious.
But what does it mean that we were wrong? There are examples that we computed the wrong number or what?
Yeah, there are examples for which, I'll show you in a second. There are examples for which you do the computation, you get a totally finite answer, and that totally finite answer has nothing to do with the real world. Okay, so that, and again, machine learning is something, the easiest way of seeing that. What is one of the benefits of thinking about things through a machine learning lens? When you're doing things pencil and paper, you are limited by the human constructs that we have in our brain. When you allow a machine to do things, it just searches some vast space of possibilities and can often give you answers that you as a human would have never even explored. And that's what this machine learning algorithm did. That's what we're going to see in a moment.
But in experiments, for example, we measure the inclusive quotient.
Yes, we do.
So we're kind of ignorant to the details of how we smooth the.
Good. So inclusive cross sections are an example of something that are maximally smooth. So the smoothness is to the max value of inclusive cross sections. And then there are things that you might have thought were smooth enough, and they're not. That's what I'll show you, and it hopefully will be pretty clear what it is. So the title of this paper with Ben and Sam, we called this "Safe but Incalculable." That is something that satisfies a yes/no definition of safety, but turns out to not at all be describing the world as we see it. That is, the non-perturbative corrections are order one. Yeah, okay.
I don't think I quite understand what you mean by smooth here, like in the mathematical sense or something more general.
I mean smoother in the sense of like epsilon delta proofs and polar continuous, and we'll see the word Lipschitz continuous come up. Like I really mean smoothness in that sense.
Of like the momentum, or is it a function of what space?
Excellent, and that's this last part of the talk as a function of the space induced by the Wasserstein metric. So you can ask, why did the people in the 1970s not understand this? And that is because they were thinking about Fock space. And Fock space is enumerated by how many particles that I have. And in the context of Fock space, you actually can't define smoothness, or rather, George Sturman in the 1970s defined smoothness in terms of smoothness in Fock space. And that's why people yelled at me in 2015 when they said, Jesse, you did a calculation that you shouldn't have been able to do. But if you think about the space not being that of Fock space, but the space that you get from the energy flow operator, which turns out to be the same space that you use for the Wasserstein metric, then you end up getting a notion of smoothness that generalizes beyond what George did in his pioneering in the 70s. Okay. But what we're going to see in this machine learning example, where smoothness becomes super clear, and then if I have time, I'll try to explain the optical transport one. But I wanted you to at least understand this super clear example.
And then, so before you mentioned charge and how that wasn't IRC safe, but I mean, clearly in experiments, that's something that's sometimes used. How does that fit into this picture with smoothness? I mean, if you're only talking about energy flow.
Right. So what it means is that things that experimentalists do with charge and charged particles are not computable in perturbative quantum field theory. However, and this is the exciting thing that Ian Moult and others have shown, is that the amount of non-perturbative information that you need turns out to be rather small. So it's not computable in perturbation theory, but those singularities can be absorbed into generalizations of a fragmentation function. And all the information that you need about a fragmentation function is something like 1 or 2 moments of that fragmentation function. So it's saying it's not safe. Oh, but the amount that it's not safe is something that can be computed in like 1 number. And this is actually simpler than if you know about parton distribution functions. That's like a whole function. But what Ian and friends are showing is that in certain cases you just need 1 number, not even a whole function. So that's super exciting. And so yes, experimentalists do that all the time. Great. They need non-perturbative input. And now the question is, does that non-perturbative input, does it completely destroy your perturbative prediction or not? Or how do you sew it together with perturbative prediction? But here we're focusing just on the cases where I want it to be really computable in perturbation theory with control. We may not care about that problem, but what I want to say is that for those of us who do care about that problem, we can still be surprised in the year 2024. Okay,
Jesse,
yeah.
earlier you mentioned some technical term about some B, some space. Can you spell all that?
So this is the optimal transport. This is the space introduced by the Wasserstein metric. And so the language of optimal transport, Wasserstein metric, you'll also hear this under the name of the earth weaver's distance. And these are terms that until our work in 2018, 2019, I had never heard of before. And it's not at all obvious that this should be relevant for quantum field theory. And it turns out to be the correct language for describing the singularity structure of gauge theories in quantum field theory. But before getting to that, I do want to just highlight this kind of machine learning way of understanding it, and then you'll see why smoothness matters, and then I can skip over. So smoothness in this space is a little bit painful to talk about, but smoothness in this machine learning context is a little bit easier. And because I'm doing it this with chalk and not with slides, that's why I'm doing it in this order. If I were giving a slide talk, I could show you nice movies that can actually make this last part more intuitive, because I'm doing it on chalk, I'll have to start with this one. Okay, so why do I want to care about machine learning for this problem? I want to care about machine learning for this problem because machine learning is very powerful at doing the following. If I give you two probability distributions, P of X and H of X, and let's say I do this by giving you these probability distributions in terms of samples. So X could be some high dimensional feature space. I'm going to now pluck examples from that according to this probability distribution, pluck examples according to this one. Then machine learning is really good at outputting an estimate of the ratio of, which way did I do it, of P of X over H of X. So the machine learning details don't matter. All you need to know is that you give me P of X, you give me H of X, I can give you an estimate of the ratio. That's all you need to know that machine learning can do. Okay, so what do I want X to be? I want X to be all, and with an asterisk here, safe observables. Or all the ones that I thought were safe. Of course, we're going to find that the punchline is going to be that these actually secretly aren't safe, but let's imagine that I have a list of things that I thought were safe. And then I want to say, well, what's the probability density in terms of P here of X in terms of parton level predictions? So parton level predictions. So I'll draw a picture for you this in just a moment. And then, oh, by the way, this is going to be in the context of quantum thermodynamics. So these are going to be in the context of QCD. And I'll just remind you about what the difference is between parton level predictions and H is going to be hadron level predictions. So let me just erase the second one. So we're going to imagine doing some collision at the Large Hadron Collider. We're going to slam together some beams. Stuff comes out. And let's say one of the particular things that comes out of the hard collision is a quark in the context of quantum chromodynamics. Just like electrons can radiate photons, quarks can radiate gluons. So my quark can radiate a gluon. And then you have more radiation, more splitting, quarks to antiquarks, and so on. And the final state viewed here, this is what I will call my parton level. So this whole process is called a parton shower. Over here, we have a hard scattering process. So at short distances, we have some hard scattering process that makes a bunch of quarks and gluons. Those quarks and gluons radiate because of the singularity structure of gauge theories. It gives you this parton shower. So here is where I'll define my P of X. And then the magic of hadronization happens, where my quarks and gluons get confined because of the strong nuclear force. And then what pops out of this is a bunch of hadrons with funny Greek names, phi naught, phi plus, kaons, so on. And this is where I'll define my agents. Okay, so I have observables here that have a definition both on parton level and hadron level objects. So I'm not going to use the actual labels pion, kaon, or quark and gluon. That's ambiguous across this boundary. But for example, the 4 vectors of the particles, I can combine them in various ways to define some observables that make sense both at the parton level and the hadron level. And this is something that I can do with simulation code. So I can build a simulation of that parton shower process and the hadronization process, pick out P of X, pick out H of X, and then use a machine learning algorithm to compute this ratio. And if X is really safe, then what would you expect? Well, what you would expect is that if you took the ratio of parton level to hadron level, you'd say that this thing should be approximately 1. Because if it's safe, it shouldn't be sensitive to the details of non-perturbative dynamics. It should be computable in perturbation theory in terms of quarks and gluons. And whatever this hadronization is doing isn't going to, this non-perturbative physics shouldn't have a big effect on what you're saying. Now, there'll be corrections. So if we started off with a quark that has some energy, this whole process is called jet formation. So we just have the energy of this jet. That maybe there's going to be corrections, but these corrections should be small in the sense that if the jet energy is high enough, high compared to what? High compared to the confinement scale lambda QCD, the scale at which quarks and gluons confine to form hadrons. This is what we would expect to see. And indeed, this is what I expected to see. Right? This is the, right? Like this is what it should look like if indeed X was safe. Because if it weren't safe, then you'd say, well, you shouldn't have perturbative control. If it is safe, then you should have perturbative control. What does perturbative control mean? It means that non-perturbative physics should be subdominant. That's what you expect. Okay, so then my collaborator Sam sent me a message over Slack. What he showed was something that was totally surprising to me. That it definitely was not close to 1. It looked totally different. So let me just pause here to see if this makes sense, what the experiment in quotes that we were doing. Obviously, this is an experiment on a computer, but an experiment of trying to see what is the impact of this hadronization.
So
Yeah.
maybe just in
Yeah.
couple of words, what is the machine learning algorithm do? What's the input and what's
Yeah, good. So the input here is going to be the phase space configurations. So this is going to be some set of 4 vectors corresponding to the final state. That's the input. And then our output will be, this is what this X is going to be an observable. So this is some function of that final state. And we're going to build this object in a way that at least naively is safe. So our output is going to be naively safe. So what I mean by naively safe, what I'm going to do is I'm going to build a particular neural network architecture that does the following. It takes all the particles, whether those particles are partons or hadrons. It's going to sum over all of them, weighted by their energy. And because it's weighted by their energy, if a particle has zero energy, that would correspond to a soft singularity. But if it's weighted by the energy, then it will be insensitive to zero energy particles, so that will make it soft safe. And then it's going to be linear, so this is going to be energy raised to the first power. And as you'll see in a second, that means that it's going to be collinear safe. Why? Because this E here, and unfortunately in the literature, the same symbol phi is used both for this and for this neural network. So this is a neural network whose name is also phi, unfortunately. That corresponds to the direction that the particle is going. So I take the direction the particle is going, I compute some function, a neural network output of that function, and then I sum it over all particles. And if I have two particles going in the same direction, then their n hats is going to be the same. And then if I have energy and energy, these don't have to be the same, but their sum is such that if they're really parallel to each other, this is the same as having one meta n whose energy itself is the sum of the pairwise energy. So this is also collinear safe as well. So this particular functional form here guarantees that things are going to be, or naively, IRC safe, because they're this observable can't tell when particles are parallel and can't tell when energies are zero. And then we slap another neural network around this thing. So this is a input, phase space, output, something that's naively safe, a particular function of those things that would correspond to my naively safe observable. And then what's the loss? The loss is some loss for which it tries to learn, well, actually, this strictly speaking, it tries to learn p of x over p of x plus h of x, which is some number that's between 0 and 1 that can be used as a classifier for machine learning applications. Yeah.
So this naively case is sometimes not rarely the same. So what is happening if this is not rarely?
That is the seminar, right? Is what is going to go wrong? Right? What is going to go wrong? Because this, and so I'll explain in a moment what it really is that's going wrong. But we wrote a paper claiming, this is with Patrick and Eric, we wrote a paper claiming that if your machine learning architecture is of this form, then you're guaranteed that it's computable in perturbative quantum field theory. That's what we said. And that statement is true in a technical sense, in that there are no singularities, but it's also useless in that you do a computation and that computation has no bearing on what the actual perturbative prediction would be. That is, it's not something where I can claim that non-perturbative physics is suppressed. And we'll see it super explicitly in just a second of what happened here.
So the algorithm is trained over.
Yeah, it's trained over my samples drawn from in this case, it's the Pythia parton shower at parton level and hadron level. I train it to distinguish between these two. If it can't distinguish between the two, if it can't tell the difference between parton and hadron, then this thing would be a half. And what the plot. So if this is really safe, this is what's going to happen, right? And the answer is no. And so I get this message from Sam, and Sam said, hey, I did this study using these objects. These are called energy flow networks. The name is inspired by the energy flow operator. These are called energy flow networks. Something that you can build out of the energy flow operator. And then what he found is, okay, this is now the classifier score. That is this object. It goes between 0 and 1. And what they found is that parton level, if I take parton level events, it's peaked near, sorry, did I do this right? Sorry, classifier score, we did it upside down. Parton level events are peaked down here. That's saying that there's a region of phase space where hadron level events don't occupy, and therefore this thing is close to 0. And then hadron level events look like this. And we have dramatic separation power. That is, you can tell whether or not you're looking at partons versus hadrons, even though naively this thing should be insensitive to that. And maybe just to say what it should have looked like. So this is what Sam made, and then Jesse's prediction, which was wrong, was that this thing should be a delta function spike that it can't tell the difference for both of these things, parton and hadron, which both just give you half all the time. And instead, you see dramatic separation power. And so the question is, how can that possibly be?
Actually, what's the axis for the horizontal and vertical axis?
So this is the classifier score. This is, I trained my, unfortunately, there's too many distributions. So this is a function that I'm trying to learn, whose output is 0 to 1. This here is the probability of the classifier. That is, now I pluck examples from parton or hadron level and I plot what this thing looks like. If it always output at a half, I get delta function spikes at a half. But because it outputs something that's closer to 0 for partons and closer to 1 for hadrons, that tells you that you have separation power. And why? Then you might say, Jesse, why are you just plotting this as a function of x? I could have done that. Or why don't you just function as a function of the input? Well, that input is some very high dimensional Fox spacey thing, which is hard to visualize. So this is maybe the easiest way of just showing that I was wrong and Sam did a calculation that said, oh wait, there is separation power. That is, this function is showing you that you can tell the difference between partons and hadrons. And now I want to understand why that's the case. Okay, so what's the explanation? Yeah.
So is there some quantity like that h over p plus h that can be plotted somewhere? It's not this plot.
That is so this is the classifier score as a function of.
Okay. I see.
This is the distribution of this thing. Yeah, so this is the x. The x is basically this thing, and now I'm plotting the distribution of that thing. If the classifier doesn't work, then this thing always be a half all the time, because it's not.
I see.
That means you can tell the difference. Okay. So what happened here? So recall.
Sorry, like this a generic plot under a certain process. So is it specific or
Yeah, it's specific to 58.2 whatever, like a particular simulation of partons and their hybridization, but you could even do this in a simpler way. You could say, take some 4 vectors and just like jiggle them around and ask, is your observable insensitive to the jiggling around? You can imagine hybridization as just kind of a jiggling around of the stress energy tensor. This shouldn't have, I would have said that this shouldn't have happened. So in some sense, like somehow we were just completely wrong about what it means for things to be insensitive to non-perturbative physics. But now I can show you that we should not have been surprised. So let's recall the collinear singularity. So again, this in the case of QCD would be a quark radiating alpha gluon. And this thing, as a function of the angle of the emitted gluon, the amplitude squared goes like d theta to theta. And naive IRC safety would say you need to be insensitive to small angle physics. So naive IRC safety, that is insensitivity, would be saying, well, I shouldn't be able to resolve that I have small angles. So naive IRC safety would be saying that whatever this observable that the machine learned, it should somehow go to 0 as the angle goes to 0 for some a that's greater than 0. Yeah. And now you can immediately see kind of what went wrong. It is true that if the angle is exactly 0, I can't tell them. So in that sense, it's insensitive. But if I'm really doing a cross-section calculation, I have to integrate over various phase space configurations. So if I'm actually doing a cross-section calculation, then I have to integrate over this singularity, including this observable that I'm trying to compute. So this is just the amplitude squared times observable thing. And one model for non-perturbative physics is that non-perturbative physics is like doing an integral where there's some minimal angle. And that minimal angle is determined by the non-perturbative scale, lambda QCD over the energy of my jet. And so now you do this integral, and you're like, wait a second. My integral goes like lambda QCD over e to the power a with some coefficient here. Uh-oh, as a goes to 0, this thing is still safe in the sense that nothing blows up. But when a goes to 0, this thing goes to 1. And this basically said, but non-perturbative physics, or lambda QCD physics, dominates. And so before, remember my goal was to have something where hadron over parton with like 1 plus lambda QCD over E to some power. But you wanted that power to be big enough such that it didn't make a big deal. And here we're saying, well, hey, there's nothing in the machine learning architecture that would stop this A from getting arbitrarily close to 0, and therefore non-perturbative physics to be arbitrarily close to dominating what you're trying to predict. Okay, so then what's the solution? So the solution, retrospect, is obvious. Solution, force the behavior at small angles, force this A, to be, let's say, greater than 1. If you do that, then the non-perturbative physics will indeed be suppressed. Of course, you can make it greater than 1/2, or if you want it to be really small, you make it greater than 2. Whatever your constraint is, you can decide what that is. And in the machine learning literature, they would say, oh, this is the same as imposing what's known as a Lipschitz constraint. So Lipschitz continuity is when, as I move things around, function outputs are bounded such that if I move things a certain distance d, the function output is doesn't change by something proportional to d. And so imposing a Lipschitz constraint on a neural network is basically forcing that the slope in all different directions is bounded with a, well, so this is to say that a really is bounded, so I can't go below 1. And so what Ben, Sam, and I did is we took our energy flow networks and just added this constraint to make it a Lipschitz energy flow network. And then if you do that, then you get exactly what you wanted before, that you can't tell the difference between parton and hadron. That is, parton and hadron, basically they're nearly on top of each other if I were to draw the output of the machine learning classifier score. Okay, so the lesson here, the lesson here is that, as I said before, safety is not about just behavior near 0 or the behavior in the vicinity of collinear and soft singularities. Safety is really smoothness. How do you approach the soft singularidity limits? And from a practical perspective, you can impose that in a machine learning context or impose that in a calculation by making sure that things approach the singularities smooth enough. And then maybe just to say, that more smooth corresponds to less impact of non-perturbative physics. And so really what we're talking about when we're talking about infrared and collinear safety, what we're talking about is insensitive or control over non-perturbative physics, and so then this would correspond to more perturbative people. Yeah, so what practical impact does this have on thinking about, say, observables? It turns out to have less impact than you might think, because even though we've never said this formally in our community, collider physicists tend to choose values of A that are either 1 or 2. That the vast amount of literature is about observables that they can be very, very complicated, but at the end of the day, as far as this Lipschitz constraint is concerned, they're basically A was 1 or 2. I did a heretical thing one time and said, oh, maybe A could be a half, which would correspond here to have kind of square root behavior in terms of non-perturbative physics. But basically, people never really explored this A goes to 0 limit. And so therefore, we didn't realize that there was this secret problem hiding from us. And now machine learning like forced us to confront it. And now in the last part of my talk, I'll just now explain a little bit about, and very quickly, just explain, okay, now how do you kind of think about these things in a more cohesive picture of what it means for something to be safe. All right, any questions before I continue?
Actually, maybe yes. How would it change if you didn't use machine learning and just did some, I don't know, just use the information from BTR, like more traditional?
Yeah. Okay, good. So let me. I was thinking of skipping this, but let me just do it that way. So imagine that I didn't have this whole machine learning thing. How would have I encountered this same problem in a more traditional way? So this is what Andrew Lakosky and I encountered. I said 2015. Sorry, now I'm looking at it. It's like 2013. So the paper that I wrote with Ben and Sam, we called it "Safe but Incalculable." The paper that I wrote with Andrew Lakosky in 2013, we called it "Unsafe but Calculable." And this was referring to the fact that I'm going to show you in a second, you have observables that are naively unsafe, but nevertheless, you actually have perturbative control. So this is how we encounter the problem kind of in the reverse. So imagine that you have observables X, and X is safe. And you have Y. Y is safe. And then someone says, compute the ratio X over Y. And X over Y is unsafe. Why is that? Well, in the language that I just gave you, the function 1 over Y is discontinuous at Y equals 0. So that Lipschitz continuity story that I told you, this is not Lipschitz continuous. So even if this is safe and this is safe, this is not a Lipschitz continuous function of these things. And so this thing should not be computable at all based on what I just told you. Okay. And yet, Andrew and I did the calculation and we got an answer. So how is that possible? And this is also saying that this story of more smooth means more perturbative control. It's not just a function of the observable, it's also a function of the way that matrix elements behave. So if you were to plot the probability distribution of, let's say, this Y, the denominator here, in fixed order perturbation theory, so you do some computing in fixed order perturbation theory, and you would find a collinear singularity. So it would appear like this. So a fixed order. And you'd say, oh yes, I have this singular behavior when Y goes to 0. Therefore, if I try to take the ratio of it, I get something that has no control whatsoever. So you get a fixed order. But if you do a so-called resummed calculation where you calculate still perturbatively, but sum a certain series of Feynman diagrams, what you find is that you find the probability distribution turns over. And this structure here is known as a Sudakov peak. Sudikoff form factor. And that Sudikoff form factor actually regulates the divergence of near zero. And so what that means is that when I was doing my integral before of d theta over theta, well, that d theta over theta, that theta was assuming that I was doing a fixed order calculation. If I actually had my resum result, then I'd have my Sudikoff form factor that would regulate near zero. And so then the notion of smoothness actually is more complicated. It's not just the smoothness of the observable, it's also like how smooth the Sudikoff form factor is that regulates it, that decides whether things are computable or not. And so Andrew and I did this calculation, which everyone yelled at us about, which was the probability distribution of x over y in certain cases, and trying to do a perturbative calculation. And what do we find? It turns out that because Sudikoff logs tend to be Sudikoff double logs, when all the dust settles, you end up finding something that behaves like the square root of the strong coupling constant alpha s. This is something that's non-analytic in alpha s, so you'll never get this from a fixed order expansion, but you will get it from a resummed expansion with some particular function of form. And with this, you would say, wait, how do I understand this? So this is an example where you run through Pythia and you find that you're very insensitive to hadronization corrections. And yet it has this discontinuous behavior. And the answer for why it's okay is because it's being regulated by the Sudikoff physics. And so it's really thinking about, in a more traditional way, not with machine learning, it's really thinking about all the various ingredients that go into my cross-section. How do they combine together to tell me my overall smoothness properties? But to now give a formal definition of what this means that I have to be able to think about Sudikoff physics, and that means that I can't just do fixed order, fixed number of particles. I have to somehow talk about 2 particles, 3 particles, 4 particles, up to infinity number of particles all together in one breath. And then when I talk about safety or smoothness, I have to talk about the continuity in that bigger space of thinking about variable particle multiplicity. So did that give you some?
Yeah, I think so. So machine learning gives you a prediction or
Machine learning finds the optimal way of distinguishing between whatever you want. In our test case that we did, it was the optimal way of distinguishing perturbative from non-perturbative. So machine learning was finding like the most serious attention. If you were going this from a more traditional way, you would just say, oh, I'm interested in studying various observables. And you would learn, if you dug in deep to these things, that whether things are computable or not, or how much sensitivity to non-perturbative physics you have or not, ends up being a combination of how smooth the matrix element is. In this case, the smoothness depends on resummation, and then also how smooth the observable itself is. Okay, so in the last 15 minutes, let me just tell you what you want, and then just. And I won't be able to actually explain it in much detail, but just tell you what you want. So at the end of the day, what you want is you want a robust definition of smoothness. And the robust definition of smoothness remarkably comes from the literature on optimal transport. Okay, so what do you want? What does it mean for something to be smooth? Well, it means that for observables, I have some observable that depends on some phase-space configuration phi1, let me call it phi a. And then I have another, and then I want to compare that to the same observable qubit at a phase-space location phi b. Then kind of smoothness would want to say, like, if I move these A and B's around, the observable shouldn't change much if the phase-space configuration doesn't change much. So you want to have something like this thing is small compared to some number of some notion of distance between phi A and phi B. And if I restore the exponent A that we've been talking about before, A is what would be known as a Holder continuity exponent. So basically this says if you have some notion of how to compare phase space points and say that they're close or far away from each other, then something will be polar continuous with exponent A if you take that distance, raise it to the 8th power, okay, multiply by some coefficient, and that the observable that you're trying to compute is similar between those two configurations. Where A is that if A is equal to 1 or A is equal to 1, then this corresponds to Lipschitz continuity. So this idea of Holder continuity, as I mentioned, was already anticipated by George Sturman in 1978. But to deal with this kind of funny situation with Sudakov peaks, you have to generalize it to a case where these two phase-space configurations might have different numbers of particles. So what George did was say, well, imagine I have n particles here, and now I move them around to have n particles in some other configuration. That you can have some kind of notion of distance in terms of soft and collinear singularities. And then he would say that things are computable if these are close. The observable satisfies them being, if these things are close, then the observables are close. And if you follow George's rule, then what I described over here can't be explained in that context. For this to be explained, you have to realize that when I have fixed number of n particles, that's actually a set of measure 0 in the space of all possible gauge field configurations, because I can have n particles, but I can radiate a photon and another photon and a gluon, another massless quanta. And so actually fixed multiplicity is a small part of the whole space. But if you allow for variable particle multiplicity, then you can now say that you're smooth everywhere but sets of measure 0, and that allows you to explain that phenomenon over there. Okay, so all you need basically is for me to tell you what the notion of distance is between phase-space configurations. And so if I were giving another hour, I would go into this in detail. So a good notion of distance between phase space goes under the name of the Wasserstein metric. In computer graphics, this is known as the Earth mover's distance. And then in particle physics, myself, Eric Metodich and Patrick Comiskey, we call it the energy mover's distance, because the thing that we're going to move around to have a notion of distance is actually energy. And so here's what this distance is. So we have a distance between phase-space points. This distance will be the energy mover's distance between phase-space points phi A and phi B. What is it? So I imagine having two phase-space configurations with some number of particles here. And I want to compare that to some other phase-space distribution with some number of particles here. And the number of particles here and here could be different. This could be 20 particles, this could be 5 particles, but I still want to have a notion of distance that can compare the two. And one way of doing this is with this energy mover's distance, where what you do is you say, I want to transport stuff from whatever configuration it is and move it to where it would be in the other configuration, and think about the cost of moving energy around from one place to the other. So what this is taking all my particles that were in phase-space configuration phi A, all my particles in phase-space configuration phi B, moving some amount of energy from I to J, multiplying by the distance that I have to convert it from between I and J from one configuration to the other, and then optimizing over all possible paths, subject to constraint that that things are positive, that is, all the energy moves from one configuration to the other, and that the flow that you're doing is a positive quantity. So again, this appears in the machine learning world. It appears in the mathematics world, and because this theta here is raised to the first power, this is precisely the thing that I would need to basically know how close am I to collinear configurations. When I have to move things around, even if I have variable numbers of particles, when I have to move things around, as long as I kind of track the motion and angle to a sufficiently high power here, I can basically control that when I have phase-space configurations that are different, that I can control how different they are. And then you plug this thing in over here to this expression over here for my distance. And depending on how close you are, this tells you how continuous your observable will be. And this is something that works even if I have variable numbers of particles in my configuration space 1, 2, or configuration space A and B. And so then what is safe to calculate? So I'll end with this. So then what is safe to calculate? And the answer is, it depends. It depends on how much perturbative control you want. At minimum, if your goal is that you get something that's finite in resum perturbation theory, if that's all you want to have, then what you want is that if the distance, the EMG between your two phase-space configurations A and B is less than some delta, then that would imply that your difference between your observable would be less than some epsilon. So it's like an epsilon delta notion of continuity. But if you want, control, but not just finite, but you want control, that is, you want non-perturbative physics to be small, then you want to have enhanced notions of continuity. Like the equation that I erased on the board, that as this distance gets smaller, you want to make sure that you have robust bounds on how far the observables are from each other. And in our paper, we have this whole taxonomy of observables that have been defined in literature. And so instead of being a simple yes/no statement, yes, it's safe or no, it's not safe, it ends up being that are you continuous everywhere but a set of measure 0? Are you Holder continuous? Are your Lipschitz continuous? And then also this interplay that we were discussing before about the interplay with how the amplitude itself is behaving. That also has an impact. Okay, so with that, let me just leave you with some kind of some last thoughts. So first, the language of safety in quantum field theory has always made me uncomfortable. Now I finally know what it means, and I know that now it's more complicated than I thought before. It's not a binary yes or no. And just because you have a perturbative calculation, that's not enough. You also want to know that you have some control over non-perturbative physics, or as we were discussing, some way of characterizing that non-perturbative physics if you want to make predictions. Second thing is that this language of optimal transport theory is everywhere in collider physics. And I don't have time to go into it today for this talk, but when people had defined many different observables in the past and things that they were doing in collider physics, it turns out that a lot of them can be secretly massaged into a form where all you're doing is calculating distances between energy configurations. And now, in some sense, in retrospect, it's kind of obvious why this was secretly the backbone of what we were doing in collider physics, because things that are related to the movement of energy turn out to be things that are generically safe. And then kind of as a final thing, I started off the talk by talking about scattering amplitudes and said, well, actually, if you want to do things in comparative experiments, you need to do cross sections. And that a particular type of cross section that's beneficial is one that has to do with energy flow. And that movement here was super important for us to understand what infrared and collinear safety really meant. But it seems to be an increasingly fruitful way of thinking about things. It moves us away from Fock space. It moves us to things that even have a definition when we're thinking about conformal field theories. And it then becomes an interesting question whether or not, quantum field theories themselves might be uniquely defined by the predictions that we have for correlators of the stress energy tensor. And again, just to advertise for the next speaker you might have in this series, Ian Moult at Yale, someone who's been really pushing this kind of line of thinking, and he's has some really great thoughts in this direction. Okay, so let me wrap things up here. Thanks very much.
Thank you. Thank you very much. Thank you, JC. Any question or comments? Yeah.
Even for this theory, this kind of distance
Makes sense.
makes sense.
Yes.
I see.
Even because, so here I wrote it in terms of space configurations, but I can actually do it in terms of like flows of energy. And then this thing, I've done it as a sum of real particles, but I can actually just replace this whole thing by being appropriate integrals over phase space configurations. So there's actually a version of this that doesn't require you to have atomistic distribution. So this even makes sense in a conformal field theory context. And that's part of why I'm saying it's like really going in the direction of maybe being a nice language for us to play with, even in more formal contexts. Yeah. Okay.
Yeah, let me see. Are there some applications of these things, maybe other than quantum field theory? Maybe the underlying certain structure, maybe either in math or something about a certain property of the, I don't know, data or something. I think it's like all your motivation originally is about the 70.
Right.
The structure behind this.
Right. So now you can ask. So it depends on what you're asking. If you're asking about this particular distance, why is this distance special? This is in general a distance between distributions. In this case, it's energy distributions, but a distance between distributions that satisfies some really nice properties. And there's a whole story I could tell you about the geometry of things that you get when you study that type of distribution. So anytime you have distributions that you're comparing, this is a good place to start. If you haven't heard the word Wasserstein before, in the machine learning literature, this shows up everywhere. Basically, take a machine learning algorithm, put a W in front of it. So generative adversarial networks, and you have a Wasserstein generative adversarial network. It ends up being a nice way of talking about, again, comparison between probability distributions or probability densities. But in terms of like how it might appear in terms of a theoretical thing, like in this case, it happens to be super closely connected to computability in field theory. And now you can ask, like, what other areas are we interested in singularity structures? And something where I have zero expertise, but I've heard people talk about is in the context of tropical geometries. And it may be that, for example, there's some relationship between that and between this and that field, but that's now way beyond anything that I have any expertise in. Yeah.
There's some question and comments from the online audience. That's cool. Yeah, if not, that we should thank Jesse.
Okay, thank you very much.
Thank you.